Okay. So once again, if you guys could just tell me that you can see and hear what I'm doing. Just a few people chat me. Okay.
Yeah, I can see that.
All right, thanks. Now, I'm not going to discuss it now, but I didn't feel that last Monday worked very well. All right. And part of it was not only did I have to have the Zoom working, the computer working, but also the projector working. So if we were all here and the projector didn't work, I could have gone to the whiteboard. If we were all online, that could have worked, right? So I'll probably send out a survey to see, is this really meeting your needs? And maybe it's, I'm not necessarily just in love with technology for technology's sake, especially right now. Oh, man. Because if you're viewing remotely, the projector stopped working again. Oh, or now it's working. Well, let's make hay while the sun shines. So what we've done is talked about synthesizing transfer functions in a variety of ways. And we introduced the DF2 methodology. Now I have, and we can go over the other methodologies, but I wanted to talk about gain bandwidth first. And the thing is the methodology that we followed with those op-amps assumed that the op-amps were ideal. But op-amps have a gain bandwidth limitation. And so, actually, why don't I kind of go over that? I was just checking that I was recording. Like, what can happen, right? Or like, what's the big picture? So let's do we're talking about a high pass filter, right? And we put that into an op amp, right? And if we do a Bode plot of that, right, we're going to have something like that. And it never comes back down, right? It's high pass. Now, with these R's and C's, does it stay high for, infinity frequency? Not really, because there's other things going on in these devices. It's just in the frequency of interest, right? But an op amp actually has a frequency limit. And if I plot it like this, all right, I can just call it AV divided by S, all right? Now we're going to get into where this comes from. I'm just trying to show you that every op-amp has a gain bandwidth limitation that roughly looks like a straight line on a Bode plot. Other things go on with it too, but this is the simplest model. So the thing is if I were to make this circuit, right, and I'm testing the Bode plot, all right, I would see this, then it's high pass, but now the op-amp is acting like a low pass. So in a sense, I'm getting what you might call a bandpass. But the assumption is that let's say at this point, we still call it a high pass, because sometimes what we can say is it's a high pass, but the information is limited to this point in frequency. So it'll work the way we want. Now, if we had information out here that we wanted, no, the circuit wouldn't work, and we would have to buy a higher frequency op-amp that maybe had the gain bandwidth out here. All right. So when we do our filters, when we do our theoretical transfer function, right, HS equals S plus omega naught, nowhere in there is the fact that this op-amp has a gain bandwidth. Now, what I'm going to do is show you how to take that into consideration, but really, this is the big deal, right? There's a gain bandwidth limitation. Just don't be there. Keep your circuit working in here, and you can have a lot of control over, like you can put filters to make sure that, yeah, there are no high frequency data that you need, or you know that you don't maybe you don't care about that higher frequency data. All right, but probably one of the biggest deviations between a theoretical op-amp and an ideal op-amp, really the number one is it's this gain bandwidth limitation here. All right, so that's a little bit of the big picture. All right. So ideal op-amp, right, has open loop gain, and it's constant for all frequencies. Infinite, right? It's infinite at 1 hertz, it's infinite at a gigahertz, right? This isn't true. Inside the op-amp, there's a capacitor. And if you remember, I think it was homework 2, where I'm talking about static or dynamic systems and whether there's a capacitor on the inside or not. Well, there it is, right? Now, it turns out there's many capacitors inside an op-amp, but this one, it's kind of big, and it's bigger than all the other capacitors, so we can kind of ignore everything else, all right? But what I'm trying to say is that we're actually getting inside the package. 122 will get even more inside the package. 124, you're actually going to start hooking up transistors and make your own little mini op-amp. All right. And the graduate course 223, you will design the transistors and hook them up in a CAD tool to make op-amps. But really, it's modeled quite simply, right? You can read this paper. And what's interesting is a lot of the op-amp performance can be set from this capacitor, right? Notice there's an S, right? Well, I have GM, which relates voltage and current. I have a voltage, I have a capacitor, and I have an S. But notice, there's only one S. An ideal integrator, an ideal op-amp with frequency behaves like an ideal integrator, okay? And so just to prove this to you, right, in LTspice, I said, all right, what if GM is 100? And then I'm going to make a Bodie plot of that. Oh, sorry, I got some chats. That's good. Same here. Oh, okay. I'm not taking attendance today. Don't leave. So really, an op-amp has two stages. It has this differential mode stage, and it gives a current, and it's just GM times VN, right? Then it goes into a pure gain stage, which has this feedback capacitor. That if we didn't have this feedback capacitor, you don't maybe understand the words I'm using yet, but what'll happen is you'll have an unstable circuit. So in fact, you probably can follow the conversation, let's say, a little bit. So low pass filter, right? Omega naught, S plus, omega naught. If I don't have this feedback capacitor there, right? And so what does this lead to? E to the minus t, right? Decaying exponential, because the root, where does this equal 0? Minus omega naught. But if I have this, which can happen if I don't have that capacitor there, I will get e to the plus t, which is exponential increase. So it just won't work. All right. So that's what I mean by you need this stabilizing capacitor. Without that, it just, the op-amp would be too hard to use. I mean, if you think about it, in your 97 and 98, you kind of use these op-amps, and you could do all these wonderful functions, and they were relatively easy to use, right? Part of that is the gain is close to an infinite, and this feedback part. Without that, you'd need, without that feedback capacitor, you'd have to add it yourself, and you'd kind of need EE132 to even put an op-amp on a breadboard. So I modeled this in LTspice, right? And notice, I have this straight line coming down, so that's some open loop gain divided by S. That's what an integrator looks like, right? But what's the phase of a pure integrator? Well, there's no real part, right? It's all imaginary because S equals J omega. So the phase is a constant minus 90, which I've highlighted in blue so that you can actually see it. So when I'm drawing those straight lines saying here's a limitation of where this op-amp can work, that's because the very first model of an op-amp's frequency response is this integrator 1 over S type functionality, type relationship. All right. Now, nothing is ideal, right? I can have this capacitor here, but there will be a resistance leaking or something, whether I want it or not, there will be a resistance. So now, if I put it through my equation, now I have GMVN divided by this feedback capacitor, right? And here's my pole, right? S plus 1 over R times my feedback capacitance. Before, it was just something over S, but no, now when S equals 0, this will all go to a finite number, all right? So in fact, you can have in a real op-amp, right, you won't have, in a real op-amp, this line will keep, in an ideal op-amp model, this line will keep going up towards infinity as we get closer and closer to 0. A realistic op-amp, you get this low pass type of function. But remember, this is 120 dB, right? The gain is quite high. And then at 10 hertz, right, we're getting the gain is going down. And here's the thing. At 0 dB, which in this case is 10 megahertz, causes 0 dB, right? That's our unity gain frequency, and that's actually what we call our gain bandwidth. So, which you can look up on a data sheet. So when you look at the data sheet, you can come up with the gain bandwidth, right? And you know to stay away from that. Now, this minus 3 dB point, normally we don't care about it because you know how we talk about the open loop gain going towards infinity? Well, really, if you have a circuit with a gain of 1, an open loop gain of 100 is effectively infinity, right? If I have a gain of 10, well, it changes a little bit, but an open loop gain of 1,000 is effectively infinity, all right? So the thing is if I'm working in this area with a gain of 10 dB, right? Right up here where it's 20 dB, right? So the thing is, I can go up to 100. Well, let's be conservative. I can go up to 100 kilohertz with a gain of 10 dB because the open loop gain at that frequency is 40 dB. So is it infinity? No. Is it acting like infinity if my target gain is down here? Well, yes. So in your 97 labs or wherever you took it, we all did the experiments down in here so that you would never run into this. Or hopefully they did that. All right. So some more things. FU is the unity gain frequency, and we can go through some algebra. And we have this figure of merit GM divided by 2 pi with that feedback capacitor. Now the thing is these are the equations you would use if you were making your first pass of an op-amp design, meaning you're an engineer at Linear, Maxim, Analog Devices, Texas Instruments, and you're trying to figure out where you want your gain bandwidth to be. That's not what this class is about, but some people, in order to learn, I can't just say it's a black box. I have to give a little bit of information, but really you won't really get the full picture until you take EE 124, all right? The big thing is this cutoff frequency is the gain bandwidth, all right? And actually, we're not worried about phase at this time. All right, so if we look at our op-amp, we have a really high gain. It's constant, okay? And the phase is actually 0. And yeah, it's a first order circuit, so the phase goes down to minus 90. But look where the line is straight. It looks just like an integrator, and the phase is practically constant at minus 90. So right here, again, this spot, the gain bandwidth is given at 10 megahertz. Now the other thing is they'll give you a value for open loop gain, which will be very close to DC. Now you can't draw a line from the open loop gain necessarily straight down in LTspice and expect your results to match, but it's a pretty good approximation for hand calculations. All right. Now again, you're just designing a gain stage. You're an op-amp designer, all right, which again isn't this course, but just so you know, the gain bandwidth is really related to that feedback capacitor, and GM comes from the transistors. All right, so here, right, we have what I would call, it's a first order low pass filter type op-amp model. And then the red line is the ideal integrator op-amp model. And see right here, they're overlapping 100%. But really at at these frequencies, if your gain is in here, the difference of an open loop gain of 120 versus 160, it'd be really hard to measure the difference, okay? So as F goes to 0, the open loop gain on the red line, yeah, it tends to go to infinity, but that's when there's no resistor with it. That's when it's just a pure integrator model. So it might not work as a great model at these very low frequencies, but you know, a millihertz signal is a very slow signal. We tend not to run into that as EEs, but if you're measuring like earthquake stuff, well, maybe you would. But in the range of interest that we tend to deal with, yeah, it looks just like an integrator, right? Even though it's not an integrator in the whole frequency range of interest. Now, how do we model this? Well, in LTspice, you can use the universal op-amp model and just say, I want 30 megahertz, right? What is that gain bandwidth when you get a part? Well, it'll tell you right there in the data sheet. Now, here's the thing. That 30 megahertz isn't like a 1% resistor where it's very tight. It's all over the place. Because you might ask yourself, hey, I've got a low-pass filter right there. But you wouldn't use it as a low-pass filter because this cutoff frequency is bouncing around due to manufacturing tolerances. Really, the way this is used is, here's the frequency limitation. If I get too close to that green line, right, my circuit's going to stop working the way I want it to work. All right. So if you just see 30 megahertz, you just know, and then you see what your gain, your maximum, your DC gain is, you can kind of come up with a straight line to stay away from, right? So it's just information for you to not be there. Okay. Any questions on this so far? Because right now, what I'm telling you is that in 98 and so far, we said the open loop gain as a function of frequency equaled infinity, right? That's been our model so far. And I'm telling you that's not true, right? The easiest model is open loop gain divided by S, right? So you just get that straight line. Now, this is an easy model to work with, but a more accurate model is this, right? All right. And then there's op-amp models with 7 poles in them, right? It can get a little bit hairy. But anyway, why do we teach this so much instead of these? Well, as long as we know this, we keep our design space, you know, well away from that line. And then it'll act like it's infinity. All right. Now, oh, Artem has a question. Wait, hold on. I got to take off my head. Where the what? Oh, the feedback line. Okay, yeah. So we assume that if data multiplies the output, we have the line like in front of, if we had it in front of a volt, then that would multiply the in. Right. So I think what Artem was saying is if I drew this picture where I had a summer, and then I had beta, and then I had avol, right? Right? If I were to, rather than write this equation, right, I would write V out equaled so what's time V in? Beta times avol. So beta open loop gain, right, times V in. Now here, this is now fed straight back in. And in fact, so now beta is in fact 1, right? Minus V out. Which, if beta were a transfer function, yeah, that's kind of what we were doing with that DF1, right? Where we had more than one integrator. Now we're saying we have open loop gain, right? And it's a constant. And now we have beta, and it's a constant. But what we can do is put the open loop gain divided by S. This is where we're headed, right? Well, that's just, it's kind of like our DF2, right? We have an in, we go through an integrator, we have a negative feedback times some constant, and there you go. All right. Now, this is just a DC picture, or open loop gain doesn't change with frequency, beta doesn't change with frequency. So I have V out equals the open loop gain, right? V out equals open loop gain times V in, right? Minus V out times beta open loop gain. So open loop gain is there in both spots. Notice there's our minus sign, right? Negative feedback. Skipped a bit of, I'm going to show that that's a missing step, right? So V out equals open loop gain V in minus AV beta V out. Then I collect the V out. Notice V out, that scale constant is 1. This becomes plus AV beta equals AV VN. Then I divide this part, and that's where I'm getting it. So that plus sign comes from this minus sign because V out is on both sides of the equation. So remember where I said, why is it that negative feedback has a plus? Well, that's because you write it out like this. Then when you solve for V out, it just becomes positive. All right. Now here's something interesting. If this term is a lot bigger than 1, if open loop gain times beta is bigger than 1, then V out just becomes V in times 1 over beta. All right. Now, what's beta? I'm going to draw this upside down. So in this is an op-amp model. Inside the op-amp is a summer and a gain stage. So I could draw an op-amp model around this. This would be my plus, and this would be my minus of it, because it does the summing. Well, notice I have R2 and R1. How much signal gets fed back? Well, it's the voltage division. So beta is R1, in this case, R1 plus R2, right? So if that open loop gain is really high, right? I get V in divided by beta, which was the voltage division, okay? Well, when I manipulate that, I'm going to get this relationship. So whereas before we might have taken the open loop, we might have used nodal analysis and this equation, V out equals AV, V plus minus V minus, right? Now we're actually using a system methodology or a flow diagram, right? And we just take our beta as the voltage division, right? It's an ideal op amp, so no current is flowing in. So we're getting that voltage division there. And when we put it into our equation and let the open loop gain go to infinity, well, we get back our original equation, right? Which was in my 98 notes, but you might not have noticed it. So, big item, we have V out. We're subtracting a scaled version of it. That's negative feedback, okay? If I were adding, right? So if I were adding this back, right, this would become negative, and the inverse, well, actually, there's no S there, so I'm just going to leave it. I'm not going to mention that. Now, before, the open loop gain was just infinity at every frequency. But now I'm giving you a relationship, S. And it's just like that DF2, where, in fact, yeah, what would that be? B1 would be coming out here, right? A1 would be fed back through here, right? And then there's the summer. Now this and this are inside the op amp, right? But this is just like an integrator. Is this an approximation? Yes, because yeah, there's, in reality, a closer model would be this. But again, remember, I kind of pointed out in the frequencies of interest, it was behaving like an integrator. All right, so now let's do it. V out equals the open loop gain as a function of frequency times V in minus beta V out. And yep, this can be a transfer function, but we're not going to do that right now. Well, now I didn't show the mathematical steps, but V out equals the open loop gain as a function of frequency times V in, 1 plus open loop gain as a frequency times beta, right? Maybe you want to see that out a little bit more, but if I take this equation, right, and say V out equals AV, right, times V in minus beta AV V out. And yeah, as a function of frequency, right? I collect the terms, 1 plus beta AV AVVN. Right. Then I divide by this. So that's how we get here, right? Now again, this might change with frequency, but if this term is bigger than 1, we get back to Vn 1 divided by beta, which would give us our non-inverting op-amp configuration. All right. So even though this might change with frequency, so what this is saying is at some frequency, this might not be bigger than 1, and then this relationship won't hold. All right. Now, again, this is a little more detail on where did I get beta V out. Kind of explained it. These notes are published. That's not what today is about. Okay. So let's just look at what's going on a little bit intuitively here. All right. I have R1 and R2, an ideal op-amp model with, some open loop gain. So R1 is fixed at 10K and R2 goes 10K up to 1 meg. So the gain should increase. And notice, the gain is flat and then it rolls off. It's flat and then it rolls off. But notice, the higher the gain, the point at which it rolls off happens at a lower frequency. And so even though we have a gain bandwidth of 30, right? So this is 10, 20, which is out here, right? That's where the gain is 0. So this spot, this line, all right, the gain bandwidth line is probably somewhere just to the right of it, right? But notice, I'm getting 40 dB gain, but at 100K, I'm not. I'm getting maybe 30 dB, but at a little bit higher frequency, it starts to stop working. So if I just turn this into a buffer, I'd have 0 dB, and I'd get 0 dB all the way out to here. Okay. So that 30 gigahertz in this particular example of a gain bandwidth, right? That's where the gain of the op-amp equals 1. So it stops working before that. But this big pattern, that the lower the gain, the wider the frequency range that you can use it. Okay. So here's an example. Low pass filter design, cutoff frequency is 100 kilohertz, gain bandwidth is 1 megahertz. Now there's something kind of cool in LTspice is that you can just type in a transfer function, WC divided by S plus WC. And the WC is 100K times 2 pi. All right. So this is an ideal low pass filter, and that's in blue. So you see that blue? It's cut off, and then this line keeps going. The phase is 0, and then it goes exactly to minus 90. Out is with an op-amp model with that integrator model for the op-amp gain. So at low frequencies, it's the same. And even as it starts to attenuate, it's the same. But at some frequency, the op-amp's gain is dropping faster than the ideal transfer gain. And then the phase even goes to minus 180. That's because even though a lot of times we'll talk about this as an ideal first order filter, you put in an op-amp, no, there's a pole in there. Artem? No, I think the gain bandwidth number, like 30 gigahertz, 10 gigahertz, that is where the op-amp's open loop gain is 1. right? So in this filter, what's the gain? 1, right? 0 dB. So the op amp has, the open loop gain of the op amp has to be 100, otherwise it won't act like the ideal transfer function. So right when it starts to deviate, that means the open loop gain of the op amp is getting below 100. Maybe it's 10, maybe it's around 10, even though the gain bandwidth is more out here. Okay, did that answer your question, Arthur? Which omega? This one? Yeah, yeah. Well, as it turns out, the cutoff frequency was 100 kilohertz, right? So this is our 3 dB point. This is our minus 45 degree phase for the ideal transfer, and it should be minus 90 degree phase for our second order system, right? And it's working. It's just when the frequency gets higher, the ideal stays at a straight line. The non-ideal starts, you can see the difference. I guess what I'm saying is up to this point, you can't tell the difference really between a first and a second order, except for maybe there'd be a phase difference, right? But then as you get farther and farther, the gains are wildly changing, okay? And here's the thing, that gain bandwidth changes a lot for manufacturing. So you might say, yeah, this is a better low pass filter. Look, I'm getting a second order filter for one capacitor. Well, maybe. But as a thing that if you're making thousands and thousands of products and they're not all working the same, you might find that you don't want to do it that way. So I talked to Josh. Oh yeah. That's an interesting thing because they both have open loop gains. The previous one, the example we'd been using is 120 dB, right? If I chain those two op amps together, well, now the open loop gain is 120 plus 120, but the frequency is falling off faster. But so you can actually improve circuit performance by chaining op amps together. But yeah, the phase would start to, you'd see a different phase. All right. So now with the high pass, again, ideal transfer function, blue, put in an op amp, and now I've got a bandpass, which is kind of what I said at the beginning of class. All right. Now, I guess, you might say that in life, eventually everything is a low pass filter. We still call this a high pass filter and not a band pass. And I think what it is we meant for this to happen. This part is causing a low pass in a way in which we cannot control. So as long as we keep our signals below here, this bouncing around won't cause us a trouble. All right. So then I do a bandpass filter, right? There's two op amps. Here's the ideal transfer function in blue. It's behaving very band-like, and then all of a sudden at the higher frequencies, it rolls off more. If you see the phase is minus 270, so I got to think about that because there's a pole here, there's a pole here, but these two op amps will add extra poles as well. So I think because it's a bandpass, I'm not getting a, yeah, if it were at second order low pass, yeah, I'd be at minus 180, but the bandpass doesn't quite behave like that, right? At the band, it's actually zero phase. And out here, it's actually at minus 90, right? And that these op amps add two more minus 90s. And that's a way you can kind of estimate how many poles are, right? It's not a perfect estimate, but take the phase and divide it by 90, and that's kind of how many poles you'll have. It's not perfect, but it gives you an idea. So if I were writing a lab report, here's my theoretical Bode plot. This is what I measured. What's the difference? I would make a circle here and say it's the gain bandwidth, limiting what's going on. You can come up with an equation for it, right? Just using AV over S. All right. Salin and Key low pass filter. Open loop gain starts at a megahertz, gain bandwidth 1 megahertz, level 1 model. So low pass, VH, it's dropping minus 40 dB per decade. The phase goes from 0 to minus 180. It's a second order low pass. Wow, that's pretty good, right? One op amp gives me 2 poles. Whereas the way we were doing it before, with the integrator structure and the intuitive structure, every op amp gave us 1 pole. All right. So we're looking at the actual circuit, and yeah, it even starts to behave like a better low pass filter, reaches some minimum, and then it rises a bit. Okay. So you might think everything is hunky-dory. You might think everything is hunky-dory. And it is. Let's do, now I'm putting in a step function and doing it in time. And notice it matches pretty darn well, right? That is a second order low pass step function response. Looks overdamped, right? All right, let's take another case. With chained op amps. All right, I'm getting a straight line. It seems to be a little bit better. So here's the thing. Look at how long it matched. Then when it didn't match, it was below the line. So when you looked at the step response, it actually matches theory and the op amp model pretty well. So that chained op amp, yep, it matches pretty well, and then it's even more low pass than what's going on. So the time domain of that's going to be pretty good too. It's going to match. But I've changed a few things. I'm using a level 2 model. The gain bandwidth is a megahertz. So this is a more realistic model, right? It's not just AV over S anymore. And notice, it matches, and then it comes above the line and goes high. This is acting almost like a notch filter. Well, the only thing that changed was this was model level 1, the easy one, right? And it said it worked. Then we did a more realistic model, and it stops working. And what's going on is there's more than one pole in here. And when the open loop gain ceases to act like it's an infinity, this, like if this op amp wasn't here, that capacitor will kind of act like a high pass filter. So it just stops working. And now look at the step response. It jumps up, it comes down. It's a mess. It doesn't work at all. All right. So yeah, silent and key filters can be great. It saves you an op amp, but you really have to understand what's going on at the gain bandwidth and choose the model properly so that you don't get this. All right. Now, the feedback capacitor was 10 micro. Now I do the same thing, but I change the feedback capacitor to 10 nano, which means I have to recalculate R. That's okay. And look, now it goes back up, but not as bad. And so the step response is better. So this is like an official war story, right? In '98, I wanted to do a project that got people excited about things. And what I wanted to do was a low pass filter that would take a signal from a microcontroller and turn it into an analog voltage, right? Because you have to admit, a lot of things are done digitally. So what is the relevance of the EE98 when there's so many digital circuits? Well, making a filter, doing power supplies. So I had done it, and the frequency and the response, while it worked, it never matched theory, right? Not only that, when I did, I didn't do a formal Bode plot. I'm just looking at the oscilloscope and changing the frequency and trying to find the in this case, the minus 60 dB point, and it's not showing up where it should. Like, that's okay. Maybe my capacitors are 10% off. Maybe these are off. So I calculate it. Doesn't explain it. It's way off. And I'm using the proper op amp model from Linear. And then, it finally hit me that while they're quoting a certain op amp gain bandwidth, when you read the data sheet and you see how much it varies, I said, oh my God, the gain bandwidth, instead of here, the gain bandwidth was limiting here. And so it was working, but it wasn't working as a second order circuit. Because, I was trying to make the highest frequency low. I was pushing the limits, and it took me a while to get it. And what I realized is, if this capacitor, like mathematically, there's a relationship between the capacitors and the resistors and the poles, right? I kept that relationship the same, but made this smaller, because when this op amp stops working, this just behaves like a high pass filter. So when the open loop gain is not effectively infinity, this is just garbage, and you're getting this, which is why I make a big screaming deal about gain bandwidth in 110 and 110 lab. Okay. Now, I just want to look ahead. You'll see me make a big deal about negative feedback. Well, here, I have V out, I have 2 resistors, and I have positive feedback. Oh, okay. Let's analyze it, right? If you say this doesn't work, well, let's prove it. all right, Vx equals the voltage division of V out R1 and R2. Okay, and I set them equal to each other. So Vx equals 1/2 V out, just from voltage division, and it's an ideal op amp. V out equals the open loop gain. Now, Vx minus V in. So Vx here is on the positive side now, and V in is coming in on the negative side. Okay, what is Vx? It's 1/2 V out. All right, so we substitute it. We magically manipulate things in algebra. But notice this is negative instead of positive, right? Okay. You substitute everything in, and damn, the gain is 2 if the open loop gain is infinity. What? How the heck that happen? I assumed it was ideal. I did instead of nodal, I did voltage division. I didn't make any mathematical mistakes. But I've been saying you can't do this for years. Well, you can't. And the reason is this DC model thing doesn't work. When you have negative feedback, it does. When you have positive feedback, it doesn't. So let's simulate it, right? Hey, well, wait a second. I'm doing a Bodie plot, and I am getting a gain of 2. And then it's rolling off. Oh, wait a second. Professor, man, what are you telling me? You're telling me you can't do that, and they're clearly a gain of 2. All right. Now we go and just do a step function, and it's starting off, and then bam, it goes up to the rail. All right, this is not working, right? Because if I put in 1 volt, I should get 2 volts out. Now I'm getting 5, and it's almost as if it's exponentially going to that. Look at the phase. 0, 0, 0, plus 90. That's positive feedback, right? So this is not a low pass filter because the gain is going from 0 to 90, right? What I have here is that if I properly modeled it, I would have so here's the thing. DC, the phase never changes, right? The phase would be 0 the whole time. So if this is coming down and the phase is going up, there's a capacitor in there, right? There's a pole in there, right? It just turns out that kind of all I have to do is take open loop gain, divide it by S, divide this by S, and I would get something like, omega naught divided by S minus omega naught. And when you take the inverse Laplace transform of that, you get exponential increase. Now you can still use these circuits as Schmidt triggers, right? And this whole idea of I'm saying you're taking the inverse Laplace transform, this is all in the notes, and you can read up on it for itself. But what it is a Schmidt trigger uses positive feedback, and that memory helps it decide whether it's going to go high or low. Because what it is that Schmidt triggers, it depends on what state it was in before it does the next thing. And how does it do that? It does it with a capacitor and positive feedback, right? So positive feedback can be useful, but not always. Now, That was a lot, right? Um, did anybody have any questions? Because I did do a video on DF2. You should be able to do the homework, right? But I know that there was a lot of information there. And today there was a lot of information about the big picture, but I didn't necessarily show you how to get anything done. Now that can be next time. But what I thought is that you would have some questions about things that now I would answer, and not just little questions, but like maybe bigger questions. So, do you have any questions? Okay. Okay. So the question was more of a what's the difference between Model 1 and Model 2 in the universal op-amp model? And I'm going to answer your question probably part way, because although it can be important, it like it might be distracting, right, to actually answer the whole thing. So I'm going to set this to level 1, okay? And the open loop gain is a meg, 10 meg for the gain bandwidth. I'm going to leave this one at level 2, okay? Um, Now, there's something I'm about to show you that it works in Spice, any Spice, but in practice, it won't work. Remember how we can have a signal kind of like too big and it'll go to the rails? It it won't do this for AC simulations. So I can put in an input of 1, even though the gain would be like a million, the output voltage would be like a million. LTspice is fine with that. So let's just simulate the open loop gain of both of these. I'm not exactly going for pretty here. So if I set the input to an AC magnitude of 1, right, the power supply would have to be huge to get that, right? But like I said, just to repeat it, the Bodhi plot part doesn't care. So, 21. Okay, so up to 100 megahertz in this particular case looks super close. So I might have to take it out farther to see the difference. Okay. So you actually, in this particular case, I have to take it out a lot farther. I think I use a gain bandwidth of 1 megahertz instead of 10 for those other examples. So you can see level 1, it's 1 pole because the phase goes from 0 to minus 90. The level 2, right, you can actually see it's behaving like a second order because here's minus 20 dB. Then at this point, it's minus 40 dB, right? And then the phase is headed towards 180. I just have to go farther. Now, why did the circuit do that crazy jumping around and all of that? Well, a first order circuit, right, that can't be under, over, or critically damped. There's only one root, right? Or one pole. But a second order, well, that can be over, under, critical. Not only that, a second order can sometimes even have, well, I'm just going to keep it simple. A second order circuit has the ability to be underdamped. And when something might, in this case, it's not underdamped, right? There's one pole up here, one pole way down here. It's so separate that it isn't until here, right, that you can tell the difference between a first and a second order system. But sometimes you can take that, put in some feedback, it manipulates these poles, and the next thing you know, your op amp starts to behave underdamped, and so it starts bouncing around all over the place. But this is the raw gain bandwidth. The Salonen key, right, you know, it had more things going on with it. Does that answer your question? Kind of? Yeah. We're going to get into writing transfer functions where, yep, our open loop gain has 2 poles. We put it in through our, we find the transfer function with the open loop gain equal to a transfer function, right? And then we determine, will the circuit be under, over, or critically damped? All right, so that's not today, it's not this homework, but it's coming. Okay. I don't C. So 10, 1, 2, 3, 4, 5, 6, 7, 8, 12, 13. All right, we're missing about 10 people. Or no, yeah, maybe even 11. Well, I'm not going to yell at the people who are here. Okay? So if there's no questions, I'm just going to stop recording.